Welcome to Lesson 7. As you can see here, we're going to calculate and understand the intuition for derivatives of trig functions. Taking stock of where we've gotten to thus far, you can see that we've really covered quite a bit. We started, of course, with the limit. Understanding the limit allowed us to define the derivative, and then we've been focusing our time on using our understanding of the derivative to find the derivative of many common functions that we're used to using. Obviously we've looked at all types of polynomial functions, constant functions, linear functions. We can take the derivative of square roots, cube roots, radical functions in general. We then looked at exponential functions, we looked at logarithmic functions, and we found a way and derived a rule for finding the derivative of any of those types of functions, thanks to the chain rule, of course. And now we're going to look at trig functions. And so after today's lesson, we really have covered probably all of the function types that you have learned thus far in your math career. So quite a bit of information and knowledge that we've gained. So you should be incredibly proud of yourself and keep working hard. Here we go. Okay, so go ahead and work through parts A and B here. And I'm going to put up part C in about 5 to 10 seconds. So pause the video before getting to part C, work through A and B, and then only after having worked through A and B should you go on to part C. Right, here comes part C. Okay, so part C is really in case you struggled mightily with part B and had trouble devising a method by which to approximate the derivative. So sketch a graph of the derivative based on what your graph of sine of x looks like, and consider what function has the same characteristics as the derivative f prime of x. And this will actually allow you to make a pretty solid guess at what the derivative of sine of x should be. So do that if you haven't already, and then we'll take a look and kind of talk about the intuition behind the derivative of sine of x before we prove it. So here is the graph of sine of x. Remember, the sine of x is the y-coordinate of the points along the unit circle, where the number of radians I've traveled around the unit circle is the input, right, or the x value. And so if I think about traveling 0 radians around my unit circle, that's the point where the y value is 0. When I've traveled pi over 2 radians around my unit circle, the y value is 1, so on and so forth. Now that I have this graph, how can I approximate, or at least conceptualize, what the derivative of this function should be? Thankfully, the derivative is a really simple concept. It's just the slope at any point. And so, using this, I can construct a graph, or a pretty accurate sketch of what the derivative should look like. And of course, we remember the strategies that we devised for doing this, and the important thing that we needed to locate where the derivative was going to be 0, and then we could look for what's happening in between. So making my sign chart of the derivative, and if I just start at 0 and we think about, okay, well, where on my function of sine of x am I going to have a slope of 0? And so I'm going to have a slope of 0 here, slope of 0 here, slope of 0 here, and so I can just kind of mark those points down. So negative pi over 2, positive pi over 2, another 0, another one at 3 pi over 2. Okay, and you could keep going, but for now this is plenty, and so we can go ahead and mark those values down on this second graph that I've constructed. And of course, these are the points where the function, the derivative function, is going to be 0, where the slope is 0. Trying to be accurate. Okay. Now what's happening in between these values? Remember, the slope of the function is what we're considering, and so in between negative pi over 2 and positive pi over 2, the slope is clearly positive. And then between pi over 2 and 3 pi over 2, clearly negative, and then past 3 pi over 2, clearly positive. We also have to the left of pi over 2, and here we can see that's clearly negative. So now I can really begin to visualize what the derivative function is going to look like. To the left of pi over 2, it's going to be a negative value. Past pi over 2, it's going to be positive. And then it's got to come back down because it's got to hit 0 at pi over 2, and then it's going to go negative, and then it's got to hit 0 at 3 pi over 2, so it's then going to be positive afterwards. And you might notice that, well, this looks kind of like it's going to be another sinusoidal function, another trigonometric function. To further confirm what we might be recognizing, let's kind of hone in and take a look at what we might expect the slope of the function to be in between our roots. And so to do that, I'm just going to construct what appears to be the tangent line at these points in between where the slope is 0. So take a look at each of these tangent lines. Here it is. What would you say the slope of each of those lines were if you were guessing? And if you wanted to make an educated guess, you could take a look at the what the rise of each of these seem to be, the change in y over the change in x. So this is clearly positive, and if you were to go between this point here and this point here, you estimate that the change in y is from about -1 to +1, which is 2. And you can see that the x values are a little short of going fully between negative pi over 2 and positive pi over 2. Now the difference between these two in the x direction is going to be a total of pi units. But this is a little short, and pi is about 3, so maybe it's about half short here and half short here, so maybe the change in x is also 2. Which would mean that the slope, give or take, seems to be about 1, positive. If I did the same thing here, I might see that the slope seems to be about -1. So I can also plot those points for my derivative. Because the derivative is the slope, so in between negative pi over 2 and positive pi over 2, at this point, the slope appears to be 1. And in between pi over 2 and 3 pi over 2, the slope appears to be around -1. And if I went over here, I could again see that this is going to have the same slope as it did over here, which is, again, +1. And at this point, I should have a pretty clear idea of what's going on. To further this, I could say, okay, the slope's also going to be the same negative value over here, or -1. But now, certainly, I should have a pretty clear idea of what's going on. And here you see, after sketching this graph, this appears to be a pretty well-known trig function. At 0 radians has a value of 1, pi over 2 radians has a value of 0, and this is clearly modeling the x-coordinate as I move around my unit circle, or the cosine. And so my hypothesis is going to be that the derivative of f is the cosine of x. So now when I go to try and prove this, I'm going to be looking and hoping that what I end up with after applying the limit definition is simply the cosine of x. Alright, let's go ahead and actually do that now. Alright, let's go ahead and try and prove this result. So we're going to let y be equal to the sine of x. That's the function we're trying to take the derivative of. And then the derivative of y with respect to x is just going to be the derivative in terms of x, or with respect to x, of sine of x. And based on the definition, we know that the derivative of a function is the limit as h approaches 0 of the function evaluated at x plus h minus the value of the function evaluated at x divided by h. And now at this point, we need to start getting a little creative. How can we represent or algebraically manipulate this numerator in a slightly different way? And we did, I think, briefly go over this identity in the summer. But it's what's called the angle sum identity, and it has to do with how we can represent the sine of an angle plus another angle. So if you have x plus h, how can we represent the sine of two angles added together in a little bit of a different way? So I'm going to go ahead and rewrite this using what's called the angle sum identity. Okay, so the angle sum identity, it allows us to rewrite the sine or cosine of two angles being added together in terms of the sine or cosine of each of the angles separately. So I can take sine of x times cosine of h plus cosine of x times sine of h, and that will give me the same value as I would have gotten from sine of x plus h. And you can go online if you want to see a proof of that. I'm sure there's one on Khan Academy. At this point, what I want to do is think about how I can rearrange my limit statements so that I can either be taking the limit of something that doesn't involve h, you notice the sine of x here, or have a limit that I know how to evaluate. So if you go back and remind yourself of the trig limits that we proved back in Unit 1, you'll notice a couple of trig limits that we talked about that I told you not to forget the derivative of, or I'm sorry, the limit of. One of them was the sine of x over x, and the other one was the cosine of x minus 1 over x. And we would like to organize this so that we can use those limits. So the first thing to notice is that this term here and this term here both have a sine of x in common. So if I were to factor out that sine of x, I'd be left with a cosine of h minus 1 over h. And then here I have an expression that doesn't depend on x and an expression that does. And if I factor out the one that doesn't, I'll be left with sine of h over h. And so that's what we're going to go ahead and do, and that's going to allow us to use those two limit statements that we already know in order to evaluate this bigger limit. So here I've done exactly that. Notice that I've starred in green the pieces that make up this green argument for the limit, and I've factored out sine of x, and I'm left with cosine of h minus 1 over h. And here I have this statement, cosine of x times sine of h over h. And since it's a sum, I can take the limit of each separately. Now, I know that I can factor out anything that isn't influenced by the variable which the limit is actually approaching, the variable that is approaching a value within the limit. So sine of x doesn't depend on h at all, and so it's going to be the same no matter what, so I can factor that out of this limit. And I can also factor cosine of x out of this limit. Really what I'm doing is I'm saying, let me take the limit of each of these separately. The limit of sine of x as h approaches 0 is just going to be sine of x, right? Because it doesn't depend on h at all. And the limit of cosine of x as h approaches 0 is just going to be cosine of x because it doesn't depend on h either. And so in doing so, I'm going to end up with a much easier to work with statement. There you have it. And notice I've underlined the pieces that I've factored out. And these happen to be the limits that I told you to never forget, the trig limits. And perhaps you've forgotten, so now is a good time to go back and refresh your memory. But the limit as h approaches 0 of cosine of h minus 1 over h is going to be 0. And the limit as h approaches 0 of sine of h over h is going to be 1. Remember, the limit as x approaches 0 of sine of nx over x is n. And so here the n value is 1, and so this is just going to be 1. So I can rewrite this statement now in a much easier form. Sine of x times 0 plus cosine of x times 1. And of course, anything times 0 is 0, and so this is equivalent to the cosine of x. So what I've proven now is that the derivative of y with respect to x for the function sine of x, in other words, the derivative of sine of x, is the cosine of x. All right, so with that being said, let's go ahead and take a look at a couple of other rules. We won't prove these, kind of be extra credit for you to do on your own, and then we'll go ahead and apply these trig derivatives. All right, so here are the derivatives of the three primary trig functions. Sine of x, the derivative of that is cosine of x, as we just proved. The derivative of cosine of x is negative sine of x, and I encourage you to try proving this one. You can absolutely do it, and you'll need those two limit statements that we talked about in the previous proof. The derivative of tangent of x is secant squared x, and tangent of x is just sine of x over cosine of x, and so we can use the quotient rule actually to find this derivative here pretty easily. So I encourage you to try proving that as well using sine of x over cosine of x, because that's what tangent of x is. And then we can apply that same idea to find the derivative with respect to x of cosecant, because cosecant is 1 over sine of x. And similarly, we can find the derivative of secant, because that is 1 over cosine. And of course, that means we can also find the derivative with respect to x of cotangent of x, because that is just 1 over tangent. And there they are. The derivative of cosecant of x, which is 1 over sine of x, is cosecant x times cotangent x. The derivative of secant of x, which is 1 over cosine x, is secant x times tangent x. And the derivative of cotangent x, which is 1 over tangent, is negative cosecant squared. And you could prove all of these actually with not too much difficulty by applying the quotient rule. So if you want to, and you say, hey, these are kind of weird, I'd actually like to prove and make sure those are correct, go ahead and do so. But you should certainly try proving the derivative of cosine of x on your own. So let's go ahead and apply these now to solving some derivative, finding the derivative of some functions that involve these trig functions here. Alright, so we're going to take the derivative of x squared times sine of x. You should be able to do this one on your own, so go ahead and knock it out, and we'll talk quickly. Here I'm going to apply the product rule. I have a function u, which is x squared, and a function v, which is sine of x, and so I'm going to take u times the derivative of v with respect to x, and the derivative of sine is cosine of x, plus v, which is sine of x, times the derivative of u, which is 2x. And so I can rewrite this a little bit. I have x squared cosine of x plus 2x sine of x. I could factor out an x if I wanted to. I don't have to, but I can. And if I do so, I have x times x cosine of x plus 2 sine of x, and that's the derivative. So I'm going to put up a couple more for you to try. Make sure that you've got top quality solutions so that you're ready to present them tomorrow. All right, go ahead and give these a try. Make sure that your solutions are ready to go for your presentation. And notice my hint on number 4.